So now you might be wondering, what is the difference between adaptive immunity and the innate immunity, which we previously discussed? Well, both types of immunity can defend the body against foreign invaders. The adaptive system is different from the innate one in that it can generate a specific response against specific pathogens. In most cases, the adaptive immunity can do the work just to eliminate the pathogen. In certain cases, the adaptive system, in addition to eliminating the pathogens themselves, can also tag the pathogens, which basically marks them for the innate system to destroy. So it does more than just doing the work itself. It also signals others that this is a target that should be destroyed. The innate and adaptive immunity work together to defend our system. When our body encounters a pathogen, the initial or primary immune response usually starts with phagocytosis, and this is with the invader being engulfed by the macrophages. It then goes from there, which is the process we already discussed, where the macrophages engulfs the pathogen and then processes it and signals other cells to come help and fight. Usually, the primary immune response is sufficient to block the infection. This is if the virulence of the pathogens are low or the body's exposure to the pathogens is not very high. For the body to launch a primary immune response, we mentioned that we needed macrophages to participate. So we have the invading bacteria here, and then it's engulfed by the macrophage. And remember, we said that after engulfing the invading bacteria, the macrophage actually processes the particular markers that are specific antigens on the surface. We can look at these blue triangles on the bacteria here, and then these can get presented to other cells, such as the helper T cells and the B cells. The macrophages are the first responders, and they not only try to contain the bad guys, but also provide descriptions to the backup law enforcement officers, if we use that analogy, for what the bad guys look like, what these other cells should be looking for when they are destroying certain targets. And then in this case, what they are looking for is the antigen. And on this figure, the antigen are these blue triangles. Once the B cells and the T cells receive the signal or the description, they will start looking. For example, one type of B cell, the plasma cells, as we previously mentioned, they're the ones that secrete antibodies that can bind to the antigen marker, then engage and eventually destroy it. For the helper T cells, it will also process the message initially passed on from the macrophages and activate other things, including B cells and cytotoxic T cells, to look for any cells that carry this marker, and when they do find them, destroy them. So this is how the primary immune response works. This whole process involves acquiring, processing, and delivering the message among many different types of cells. Therefore, it can take a relatively long time for our body to launch this. And before this response can become active, so while we're developing this response, the invaders could still be spreading out and causing more damage. This response needs time to react, and it can only react so fast if it's the first time encountering the pathogen. After the long process of developing primary immune response, our body will remember, since we have those memory cells, what the pathogens are like. Our immune system will have this memory of dealing with a certain pathogen in our past with this particular antibody and these types of cells. This is so in the future, if we encounter the same types of pathogens with the same types of antigen markers, then our system will check the database and see that this is one that had the prior record. We know what it does and how it was taken care of the last time, so then we can go ahead and launch the same attack. In the secondary response, it is much quicker because it does involve memory cells. And those were the cells that remember what the pathogen was like previously. So compared to the primary immune response, the secondary response is much quicker. We don't need to start from the very beginning. We just need to pull out the record and see what worked and what didn't work in the past. This would be an obvious advantage to dealing with reinfection. And the results can also be longer lasting. This means launching a quicker, longer lasting secondary immune response based on memory that the immune system has, and this is actually the foundation for immunization. We know that immunization is when someone receives a shot or a vaccination, and this will hopefully give the person defense or immunity against the disease they are vaccinated against. So let's go into a little bit more detail about exactly what immunization means. This here is actually a quote from Dr. Wong based on his research and understanding of the mechanism behind immunization. Immunization is a controlled, artificially induced primary response by vaccines that enables the body to launch a quicker, more effective secondary response against real pathogens. So I think this sentence does a great job of encompassing how vaccines work. So let's go ahead and pick out some of the main parts here. First, immunization is a primary immune response. And we know that this response takes time to develop, just as we mentioned. It involves macrophages, B cells, and T cells to coordinate, then develop a memory and keep it on record. By its nature, immunization is a primary immune response. However, this primary immune response is different from what we would naturally encounter in our environment. It is controlled, it is artificially induced. So we go to a clinic or a pharmacy to get a shot. The nurse or pharmacist will sterilize our skin and then give us the shot. Although we may have certain reactions, for example, we might be fatigued or have a low fever in some cases. However, the vaccine will not make us very sick. Therefore, it is a controlled and artificially induced primary response. Immunization then enables the body to launch a quicker and more effective secondary response against real pathogens. So the real pathogens correspond with the vaccines. The vaccines trigger the primary immune response, which doesn't make us really sick. For example, if we get a hepatitis vaccination, we won't develop hepatitis because of it, and this is the point of immunization. The goal or purpose of vaccination is to give people the vaccine to induce this primary immune response, and hopefully the individual systems will develop the memory, and this will resemble the real pathogen. So that when we finally encounter the real pathogens in life, although we haven't been infected by them before, we will already have the memory of the features of the pathogen recorded in our immune system, and we receive this record from the vaccine. So this real encounter or exposure to pathogens is seen by the immune system as a reinfection. It is able to recognize it as something that it has seen before, and it already knows how to deal with it. So now we know how to make the antibody against this pathogen. This removes the disadvantage of having to wait for a long period of time for the immune system to develop memory naturally from a natural primary immune response. Please review these definitions of primary immune response and secondary immune response to understand the mechanism of immunization. And interestingly, immunization is a relatively new practice in the medical field. So this statue here depicts the British Dr. Jenner, who was credited with developing the modern immunization system. This statue actually depicts him vaccinating his own son against smallpox. However, the idea of getting something from people or even animals that already had the condition and survived, and then giving it to prevent infection is actually not a unique discovery by the British. In many places all over the world, people have been practicing it for a long time. For example, this here is actually a depiction of how to vaccinate people against smallpox as part of a Chinese practice. Actually, in Chinese literature, this practice was active as far back as the Han Dynasty, which was more than 2,000 years ago. So the idea is not really recent. However, the science that gives us the quantifiable evidence is definitely more modern. But the concept behind vaccinations has been working well for thousands of years. So we do have different types of immunization or vaccinations. We have passive immunization or vaccination. And in passive immunization, the preformed antibodies are transferred from one individual to another. For example, a child may be given a shot of immunoglobulin that we isolated from some other individuals. In this case, the preformed antibodies are being transferred, and these are already active. So immediately after the shot, the recipient of the shot will develop immunity against whatever the immunization was for. However, because it was a preformed antibody, which is a protein with a set lifespan, this fast-acting immunity is also short-lived. This is because unless the individual develops the ability to produce the antibodies themselves, once the preformed antibody wears through its lifespan and dies off, then the immunity is gone. There is also a major risk for some people getting these preformed antibodies, and this is serum sickness. So if you think about it, we are injecting the person with active immune molecules from another individual. So this is a foreign molecule in nature to the person who's being injected. Therefore, the recipient may have a reaction to these antibodies. And unfortunately, this can be really severe in certain cases. So it would be good to also be able to develop a longer lasting immunization. And this would be the active immunization. In this type, the body is stimulated to eventually self-generate those antibodies to work against the pathogens. This obviously takes longer because, if we remember, this is a primary immune response, so it will take time to develop. For example, some types of flu vaccinations may take up to a period of 4 weeks to allow the recipient to develop immunity. During that 4 weeks, from the time the shot was given to the time of immunity, people can still get sick. And we often hear people complaining, saying that the flu shot didn't work. Maybe they got it 2 weeks ago and now they have the flu. Well, this actually means that they received the shot too late. There is an incubation period, so they may have already been exposed to the flu virus prior to the vaccination. And then once they do get the vaccination, it takes time to develop the immunity. So unfortunately, the immunity did not develop early enough to protect that individual from the time of the incubation period to the acute phase of the protein where they're experiencing the signs and symptoms. So this is not because the vaccination didn't work, it's because the shot was given too late. So for vaccines, we want them to have a controlled, artificially induced primary response, and we also don't want people getting sick from receiving the shots. So depending on the microorganism that we are trying to protect against, we may use live vaccines, or we may use a vaccine that contains pathogens that have already been killed. Remember, pathogens can cause disease by secreting certain molecules like exo or endotoxins. And these toxins may still be active after the bacteria are killed, and then they might serve as the pathogens that make us feel sick. Therefore, in these cases, we could give the individual dead bacteria or even part of the bacteria, which would be enough to stimulate the immune system, but without the living bacteria, it won't cause a real infection. Or we could use what is called an attenuated vaccination. This is where we use a portion of the pathogen so we can reduce the exposure of the pathogen to the point that it's strong enough to stimulate an immune response, but it is not strong enough to make people really sick.